Hello everyone, welcome back to Chem Story. Today, we're kicking off the lecture with a really important topic in molecular polarity. Let's talk about dipoles, and more specifically, dipole moments. This idea helps us understand how electrons are distributed in a molecule, and why some molecules are polar while others aren't. It's a key concept that shows up over and over again in organic chemistry, so let's make sure we really understand what it means. A dipole is what we call a system with two equal but opposite charges, and they're separated by some distance. You can picture it kind of like a tiny magnet, with a positive side and a negative side. In molecules, this happens when one end becomes slightly positive, written as delta plus, and the other end becomes slightly negative, written as delta minus. That separation of charge gives rise to what we call the dipole moment. Now, the dipole moment is a vector. So that means it has both a magnitude, or how strong it is, and a direction, which way the electrons are being pulled. Now let's talk about the dipole moment of a single bond. We often call this the bond dipole moment. It basically tells us how polar a bond is. The more charge separation you have within a bond, the stronger the dipole moment. And we can actually quantify it using a simple formula, mu equals Q times R. Here, Q is the size of the charge, and R is the distance between the charges. Since the dipole moment depends on both the amount of charge and how far apart those charges are, a longer bond can give you a bigger dipole moment, but only if the charge separation is still significant. So it's really about finding that balance between how much charge is being pulled and how far it's being pulled. Now let's take a closer look at a few common bonds. We'll look at how their dipole moments compare and what kind of trends we can spot. Starting with the hydrogen-containing bonds, the dipole moment increases in the order Hc, Hn, Ho, and Hf. The main reason for this trend is electronegativity. Fluorine is the most electronegative, so the Hf bond ends up with the strongest dipole moment. Carbon is the least electronegative of the group, which is why Hc has the weakest. Now, bond length does play a role, but we have to consider it alongside electronegativity. A short bond with little charge separation might not have a strong dipole moment, but if there's a large difference in electronegativity, that can still create a strong dipole. For example, Hf has the shortest bond in the series, but because fluorine is so electronegative, the dipole moment is still very strong. On the flip side, Hc has a longer bond, but the charge separation is minimal, so its dipole moment is the weakest. Now let's shift to carbon-containing bonds, Cc, Cn, Co, and Cf. The trend here is similar. Dipole moment increases in that same order. Cc has no dipole moment at all, since the two atoms are identical, so there's no charge separation. With Cn, there's a small difference in electronegativity, so the dipole moment is relatively weak. Co is stronger, and Cf is the strongest, again, because fluorine is the most electronegative. But here's an interesting point. The Cf bond is very short. Even so, the large electronegativity difference makes up for that, so the dipole moment is still quite strong. Now, let's take a closer look at the halogen bonds, specifically Hx and Cx, where X stands for a halogen atom like fluorine, chlorine, bromine, or iodine. We're looking to spot some trends in their dipole moments, starting with the hydrogen-halogen bonds. The dipole moment decreases in the order Hf, HCl, HBr, and Hi. Now, this trend is mainly driven by electronegativity. As we move down the halogen group, from fluorine to iodine, the electronegativity drops off pretty significantly. That means less charge separation and weaker polarity in the bond. Sure, the bond length also increases from Hf to Hi, and that could increase the dipole moment. But in this case, the decreasing electronegativity has a bigger impact. So overall, the dipole moment steadily drops as we go from Hf to Hi. Now let's move on to the carbon-halogen bonds. Here, things get a little more interesting. You might expect Cf to have the strongest dipole moment, since fluorine is the most electronegative, and that's partly true. But remember, dipole moment depends on both electronegativity difference and bond length. The Cf bond is extremely short. So even though fluorine pulls hard on the electrons, the distance between the charges is small. That limits the overall dipole moment. Now, if we look at CCl, the bond is longer, and that longer distance allows for more separation between the charges. So even though chlorine is less electronegative than fluorine, the greater bond length helps increase the dipole moment. In fact, it turns out that CCl actually has a slightly larger dipole moment than CF. After that, the trend continues to drop with CBr and Ci, as both electronegativity and effective charge separation decrease. The dipole moment is a vector, which means it has both a magnitude and a direction. The magnitude tells us how strong the polarity is, and the direction shows us where the electrons are being pulled. In other words, the direction of charge separation. It always points from the less electronegative atom, the one with a partial positive charge, delta plus, toward the more electronegative atom, the one with a partial negative charge, delta minus. To show this visually, we usually draw an arrow. The tail starts at the positive end, and the head points toward the negative end. That arrow tells us which way the electrons are shifting or being displaced within the bond. Dipole moments are measured in a unit called debye, written as capital D, and it's the standard unit we use to express how polar a molecule is. Diatomic molecules can be either polar or nonpolar, and it all depends on whether there's charge separation between the atoms. Take polar molecules like HCl or HBr. In these cases, the two atoms have different electronegativities, so one pulls on the electrons more than the other. That creates partial charges, delta plus and delta minus, and gives the molecule a dipole moment. But if you look at nonpolar molecules, like H2 or O2, the two atoms are identical, so they share electrons equally. There's no uneven pull, no charge separation, so there's no dipole moment. The electron distribution stays perfectly balanced. So far, we've been focusing on individual bonds, but what about the whole molecule? A molecular dipole moment tells us about the overall polarity of a molecule. And this depends on two things. First, whether the bonds themselves are polar, and second, how those bonds are arranged in space. In other words, the geometry of the molecule. Here's the key idea. Even if a molecule has polar bonds, it doesn't automatically mean the whole molecule is polar. If the bond dipoles are arranged in a way that they cancel each other out because of symmetry, then the molecule ends up being nonpolar overall. So both bond polarity and molecular shape have to work together to create a net dipole moment. One really helpful way to analyze dipole moments is by using a structured drawing method, especially when we're dealing with tetrahedral molecules. Here's the idea. You start by looking at how many identical substituents the molecule has. If there's only one unique substituent, we place it on the solid line that points upward in the plane of the paper, so it's easy to spot, and we can clearly visualize the direction of the dipole moment. The other three, which are identical, are arranged symmetrically around the central atom. They go on the wedge, the dash, and the other solid line, forming the base of the tetrahedral structure. Now, if the molecule has two identical substituents, like in dichloromethane, we place both of them on the two solid bonds that lie in the plane of the paper. That way, they act as a kind of visual anchor, making it easy to see how the remaining groups are arranged around the central atom. The other two groups go on the wedge, and the dash pointing out of and into the plane, so the overall tetrahedral geometry is preserved. For molecules with three identical substituents, like chloroform, we place those three identical groups on the three lower bonds, one solid line, the wedge, and the dash. That forms the base of the tetrahedron. Then, we put the one different group, in this case a hydrogen, on the solid bond pointing upward, so it stands out clearly. If all four substituents are identical, like in methane or carbon tetrachloride, the molecule is completely symmetrical. The bond dipoles cancel each other out, so the molecule ends up being nonpolar. So in short, when one, two, or three groups are identical, the dipole moment depends on how they're arranged. But when all four are the same, symmetry takes over, and the dipole moment disappears. Polar molecules are the ones where the dipole moments from all the bonds don't cancel each other out. So instead, you end up with a net dipole moment, a clear direction in which the electrons are being pulled. This happens when there's an uneven distribution of electrons in the molecule, and that usually comes from differences in electronegativity between atoms, or from lone pairs on the central atom, which can bend the shape of the molecule and affect the symmetry. So even if the bonds themselves are polar, what really matters is how everything adds up in three-dimensional space. For example, Polar molecules like chloroform, water, and ammonia all have measurable dipole moments. Chloroform has a dipole moment of 1.1 dBi, water is about 1.85 dBi, and ammonia comes in at around 1.47 dBi. On the other hand, nonpolar molecules are the ones where all the bond dipoles cancel each other out, so there's no net dipole moment. Everything balances perfectly. This usually happens when the molecule has a symmetrical structure. That symmetry allows the electrons to be evenly distributed across the entire molecule, so there's no overall pull in any one direction. Even if the bonds are polar, the way they're arranged can cancel out the effects, and the molecule ends up being nonpolar. Nonpolar molecules like carbon dioxide and carbon tetrachloride have dipole moments of 0 dBi. That's because their bond dipoles cancel each other out, thanks to their symmetrical shapes. So as you can see, understanding dipole moments helps us explain a lot of important chemical properties, like solubility, how molecules interact, and even how reactive they are. Alright, that wraps up today's lecture on dipoles and dipole moments. We looked at what creates a dipole, how charge separation, bond polarity, molecular geometry, and symmetry all work together to determine whether a molecule is polar or nonpolar. If you've got any questions or want to go over something again, feel free to ask. Thanks for your attention, and I'll see you in the next lecture.